So now that we've gone through what electrostatic charges are as well as Coulomb's law, we want to move on to electric fields. So with electric fields, we're going to be able to calculate the electric field a certain distance away from an electric charge. And most importantly, we can expand on our knowledge and also calculate the electric field a certain distance away from a collection of charges or a charge distribution. Once we move from a simple electric field to charge distributions, that's when we'll need our knowledge of calculus and integration. So let's first start off with the idea of an electric field and what it means. And the analogy I like to use is the one with a gravitational field. So far we've talked about the electric force as an action at a distance force. So 2-point charges, you have one over here, and there's going to be some sort of attractive or repulsive force between the two objects. Now, if we compare it to a gravitational force, we have one mass and we have another mass 1 and mass 2. Usually, mass 1 is going to be in a gravitational field produced by another mass. So similar to this diagram here, you have one mass, which is the Earth and the Earth's surface, and you have a gravitational field around it, which is attractive. Not really attractive, but it's going towards the Earth. Now you have an electric field. Imagine this mass, or our Earth, is now either a positive or a negative charge. So an electric field is going to be one that surrounds an electric charge and exerts force on other charges within that field. Just like we have a mass over here from the Earth for a gravitational field, and ourselves or other objects within that field will experience gravity. So over here, the next step is to visualize these electric fields and what they look like. So electric field lines are continuous lines, and we can trace out field vectors at various points and connect the lines. So what this tells me is that there are two different ways to visualize electric fields. We can actually use vector form, where you take a look at different points, a certain distance away from the point charge. So you have a positive point charge here, and you can see a bunch of dots around that charge. For each dot, you have a vector, and you can see that the magnitude of the vector decreases as you get farther away. So this is called a vector form of an electric field. Now, if you connect the dots and just have a continuous line going out, you end up with a diagram like this. So these are called continuous field lines that have the same direction in an electric field. The closer the lines are together, the stronger the electric field. So these are just two different ways that electric fields can be visualized, and both are okay to use. For the purposes of this course, it's just a lot easier to use continuous field lines, and I'll explain why through the next few examples that we go through. So drawing electric field lines, how do we draw them? Typically, we usually use 8 lines to correspond to one charge of magnitude Q. So if I have one positive Q charge here, then I have 8 lines, 1, 2, 3, 4, 5, 6, 7, 8. Now if I have plus 2Q, then I have double the amount of lines. If I have negative Q, it's always going to be attracted, so we have lines pointing inwards. Now, why are lines pointing out and in for positive and negative respectively? We always take a look at what we call a test charge. So if I have a test charge and I bring up a test charge close, we have to make a choice. Do we always consider the test charge to be positive, or do we consider the test charge to be negative? So in that case, we always have a positive one. And if we bring a positive charge in, it's going to experience a repelling force. So that's why these arrows are going out. Now, if I bring in a positive test charge to a negative charge here, then there's going to be an attractive force, which is why the electric field lines are pointing inwards. So hopefully that helps with the explanation of why the field lines go out and in. Now we take a look at what happens when we combine two charges together. We now have a plus Q charge on the left side and a minus Q charge on the right side. You bring them close enough, you take a look at the previous diagram here, basically take out the middle one, and you kind of bring them closer and closer. Slowly, you'll start to notice that these lines will merge together, and you can combine them into a graph like this. So this would be a full electric field map of the two charges that are close together, a positive and a negative one, where you have an attractive force between the two of them, where the electric field line always goes from positive to negative. Now, what happens if you have electric fields? What happens if you have two positive charges? Now you have repulsion in the center. And so the lines really shouldn't be connected because there's no electric field line going from a positive to a positive charge. An electric field line will always have to go from a positive to a negative charge. So essentially, in this middle axis over here, you're going to end up with nothing. It's just going to be repulsion. So the way to draw this would be like this, where you have a repelling force and the lines do not cross and they're just going to bend out. So that would be when two positive charges are brought close to each other. Now, the next thing I want to mention is what happens if I drop in a positive charge here. When I drop in a positive charge in a pre-existing system with electric field lines, the positive charge will always move along the electric field. So if I drop an electric charge over here, a positive test charge, then it's going to travel along these electric field lines. A negative test charge will go against the grain because it'll be attracted. So it's just something to keep note of. So now that we at least know what electric field lines look like, we should try and figure out a way to measure the electric field. So we take a look at a point charge Q in space. So that's my point charge Q. We're going to put in a positive test charge, which we call plus Q over here. And we're going to define the electric field due to Q at a point P over here as the force per positive unit test charge, assuming our charge is very small. So the idea is we want to figure out how much force this point charge is going to feel per unit of positive test charge. So that means we're going to have a force divided by Q. But we also want Q to be very small. So we say Q approaches 0. So we're going to take the limit. The electric field is defined as some sort of force over Q. And as Q approaches 0, you can assume that you have KQ over R squared because the Q becomes insignificant and cancels out anyways from these two. So now you have an updated equation for the electric field. It's E equals 2KQ over R squared, or F over Q. And because you can relate force to the electric field, you can also define the electric force as F equals to Q times E. So these two equations are very important when it comes to working with electric fields and also other equations down the road. So what happens with multiple charges? It's pretty much the same as electric force. You do add them up vectorially. So then you're going to have the total electric field being the summation of all of the electric field components felt by all the different charges at that one point. So going back to that first example where we had the three charges and we had a net electric force felt by that third charge at the very bottom, we now also have a net electric field or a total electric field being felt by that third charge. So this is a summation. It is going to be very, very difficult in some cases to use a summation to calculate the electric field. So it's very important for us to be able to integrate. So where does this come in handy? If you have an object, whether it's a sphere or a cylinder or some kind of symmetrical object, and you want to figure out the charge distribution and also figure out the electric field a certain distance away from that 3D object, then you're going to have to break up that object into very tiny components. So I have a better picture on the next slide. So let's say you have this object and you want to figure out the total electric field felt from this object at point P. This object has some sort of charge distribution, but you also can't consider it a point charge. It's more complicated than that. But this object is made up of many different point charges. So you can break up this object into many tiny little pieces called dq. So each small piece holds a small charge. So I call this like a baby charge. So at this point, you have some sort of mini volume holding a mini charge of dq. Here you have a mini volume holding a mini charge of dq. Each of these dqs are going to contribute to a tiny component of the total electric field, which we call dE. And so that differential element dE is what we're going to integrate to get our total electric field. So the whole goal of this subchapter is to get us comfortable with setting up equations so that we can calculate the electric field, and we work backwards. So if we want to find the electric field, we first find the differential element for electric field, and that comes from an understanding of what dq is defined as well as how to calculate that volume element, which we discussed in an earlier chapter. So moving on to electric field calculations, if there are an infinite number of dqs so that we can become more accurate with our measurements and calculations, then the vector sum of all of the dEs is an integral defined as the following. So E is equal to the integral of dE, but we know that dE is itself an electric field. So an electric field is going to be kq over r squared. And when we talk about kq, it's not the total charge, but rather a mini charge that causes dE. So we have k dq over r squared, and now our job is to figure out what dq is equal to. After that, there's also something that's missing, the bounds of integration. So this is where we have to read the question carefully, analyze the scenario, and then find what bounds work best with our situation. So the next part really is, now that we kind of know the flow that we have to follow to solve for the electric field, we need to look at charge densities. So let's take a look at the different charge densities in different types of shapes. There are essentially three different types of shapes that we can look at. There's linear, there's surface or area, and there's volume. For linear, we know that there's going to be a small differential length element which will hold a small differential charge dq. So that dl component has a dq component. If we ever want to figure out the total charge along this line, if it's a uniform charge especially, or if it's not, the total charge is going to be the integral of rho L, which is the linear charge density, multiplied by it's the integral of rho L dl. So you have a charge density multiplied by a certain change in length, and that gives you a total of a total charge dq for that tiny little piece of your string. So your total charge is just going to be the integral of rho L dl. Hopefully that makes sense. Now, this is where it gets tricky. Rho L may not always be a constant. So if the question says that rho L is dependent upon something else, then you have to make sure you don't factor it out of the integral. The only time you can factor it out of the integral is if the question specifically says that your charge density is constant and uniform. In that case, your rho L is essentially rho naught, or a constant, and you can essentially just factor it out to have rho L times the integral of dl, which is the total length capital L. So then you'll be able to actually figure out what the total charge is without integrating rho L's equation. Next, you also have surface area. And so surface area requires ds. So remember our conversations from before. If we take a look at ds, it is going to be a patch on that surface. It's an area element. So now you need essentially two differential elements, either dx and dy or something like that. But in our case, we're just looking at this in a very simplistic view. If we want to figure out dq and then figure out the total charge q, then we take a look here and we see that a surface charge density rho s can be considered here, and we take the integral of a charge density multiplied by the differential surface area element, and we get dq is equal to rho s ds. So very similar thought process, and then you end up with the total charge being the integral of a surface area density, charge density, multiplied by the surface area, so that the area component essentially cancels each other out and gives you a charge. Finally, you have a volume charge density, so that's rho v. If you have a dv over here, which is a small volumetric element, it will hold a small dq charge. But if you have a volume charge density, you can say that the dq is equal to rho v dv. So hopefully all three of these make sense, and they kind of follow suit with each other, where you have a linear charge density multiplied by a linear differential element. You have a surface charge density multiplied by a surface area element, and you have a volume charge density multiplied by a volumetric differential element. Those are the three different equations that you would have to use to figure out what dq is, and then move forward with your calculations. So this will all come together as we work through practice problems together. So once you have dq, what's the next step? Now, the approach to finding the electric field requires you to choose your coordinate system, whether it's 1D, 2D, or 3D, and which way is the best, whether it's spherical, polar, cylindrical, or Cartesian coordinates. Next, you have to find dq using one of the methods we had before. Once you have dq, then you can use the equation from a few slides ago and find dE. And once you find dE, this is where it gets tricky, because sometimes most of these calculations are going to be very methodical and also very tedious. For every single calculation that you do, you have to consider the fact that your dE is a vector, and that means your vector is going to have components in different directions. So every time you calculate dE, you have to also consider the x component of dE, the y component of dE, and the z component of dE. Now, sometimes, and in most of the cases, you can see the components cancel each other out due to symmetry. And so we're going to see through the next few examples how to leverage symmetry so that we can just not do as many calculations and save ourselves a lot of work. Now, the next thing to be aware of is the fact that these calculations that we will do in the next few slides, they are going to be extremely tedious. But once we learn Gauss's law, it will become a lot easier. So for now, we have to start from scratch, but at the very end, we can use Gauss' law to save us a lot of time. And of course, at the very end, when you're presenting solutions for electric fields, remember electric fields are vectors. Your answers must have a magnitude and a direction. When we're talking about electric field calculations, there are two ways of going about doing it. The first one is going from first principles, so that's what we're going to do in the next few practice problems. Now, keep in mind, these practice problems are to derive equations for us to use in the future. So will you be tested on the derivations and these types of problems? No, you will simply just have to understand why we approach things in a certain way and understand the concept behind the derivations. So in terms of calculating the electric field a certain distance away from different types of objects, we can have linear objects, we can have surface objects, and we can have volume objects. So we're going to first start off with a linear one called a uniformly charged rod. So basically in orange that you see here, there's an orange stick. It's a linear stick, and we want to figure out the electric field a certain distance away from the edge of that charged rod. Once we do our calculation and our derivation, we'll end up with an equation that we can use in the future in case we have to solve a problem similar to this. Now, if you ever do have to find the electric field of an object that isn't one of these types of problems, then I would recommend you using Gauss law or something of that nature to make things a lot easier for yourself. Okay, so this problem says there's an electric field that exists near a straight thin rod of length 2a, uniformly charged at lambda coulombs per meter. Assume that the rod is placed along the y-axis, centered at the origin. So we have the origin here, and we have the total length of this being 2a. So 1/2 is centered at the origin. Find the electric field at any point on the x-axis. So on the x-axis, we're just going to randomly choose a point P marked out in black over here. So this would be our arbitrary point. So how do we approach this? In order to find the total electric field that is felt at point P, we have to find out the contribution of each tiny piece of the rod along its entire length. So we actually divide this rod up into tiny pieces. Like this. And we just pick one of these sections. So in this case, we picked this section in blue to be marked up as dy. This dy is going to hold a specific charge dq. So I'm just going to have a little arrow here and say that this length element holds a charge dq. And just remember, we were able to define dq in the past by saying dq is equal to rho L dl or rho S ds or rho V dV. Now the important thing here is which one do we choose? We know that we have a differential length element, and we know that it is a linear charge density. So the one that makes sense is this one. So when you're trying to pick which dq to use, make sure you pick the correct one. So we know dq has to be rho L dl, but we also know rho L is equal to lambda, which is the linear charge density. And we know dl is equal to dy in this case. So just keep in mind, sometimes the variables may change. So these are the two that we will move forward with. Now, the next step, I'm just going to move this up, is to determine the values and bounds for integration. So this is where we start getting into all the small details. The first thing we should do is find dq and de. So first step, find dq and de. once we know dq and de, then we'll be able to integrate de to get to the total electric field E. So we already know that dq is equal to rho L dl, or in this case, it's lambda dy. Okay, so next, we do want to see how we can break down dE. So over here in purple, we already have dE, and we should probably figure out its component form. So this is dEx, and this is dEy. So never forget that dE is a vector, and we have to break it down into its components as well. So with that, we also know this has a degree of theta. And the next part gets a little bit tricky because we either use trig functions or we use component vector form to do our analysis. So let's see how best to explain this. We have Ri, which is this over here. We do want to do an analysis of this, and so that unit vector is equal to xi, yi, oops, not yi. Just keep in mind this is actually going towards the right in a positive fashion, and then it's going down in a negative way. So we have minus yi for the direction, and then it's going to be hypotenuse, which is xi squared plus yi squared. Now, if I want to break this down into its x and y components for the unit vector, because dE is a vector, we have our ix being equal to xi over the square root of xi squared plus yi squared. And you also have riy equal to yi over the square root of xi squared plus yi squared. Okay, so now the other thing I want to mention is even though you can use component form, you can also use trigonometric identities. The reason why I have this theta over here is because if you take a look at this, the cosine of theta I is equal to adjacent over hypotenuse. And the hypotenuse over here, let's just write that down. The hypotenuse over here is going to be equal to xi squared, the square root of xi squared plus yi squared. So since cosine of theta is equal to xi over the square root of xi squared plus yi squared, I can technically replace this with cosine of theta 1. Now, I can do the same thing with sine. I can have sine of theta I is equal to yi over the square root of xi squared plus yi squared. And I forgot this over here is actually negative. So this would mean this is negative sine theta I. So there are two options for you to use. You can use component form in purple, or you can also use trig form in green. So in other words, if I were to rewrite dE, let's just go over here. If I were to rewrite dE, especially dEi, then it would be equal to k dq over r squared, and r squared would essentially be Ri squared, dotted with Ri hat. So this would give me K dq over xi squared plus yi squared times xi negative yi over the square root of x squared plus yi squared. Or it could give me the same thing, but we just replace this xi and negative yi by cos theta and negative sine theta. So each point is going to, each dy is going to give a differential electric field element of the following. So this dE is the contribution to the total electric field from a dy component in the length, in the charged rod. So I now have dE, but what I really want to do is find the electric field. So that means I have to figure out what my integration bounds are. So now that we have dE, find the bounds of integration. So if we take a look at this, it's linear. So we have dE dependent upon dq, but we can't really integrate or find bounds for dq. So dq is dependent upon dy, and so now we found our bounds for integration. We have to look at dy, and we know that dy goes from negative a to positive a. So that means we integrate with respect to y from negative a to positive a, which would be the total length. Okay, so next one. Now we're trying to find the electric field at any point on the x-axis. Okay, that gives us enough space to do it. So how do we put this together? We have to try and figure out a way to set up this integral. So we want to solve for E is equal to the integral from negative a to positive a of k dq over ri squared ri hat. But we know k is a constant, and we also know lambda is a constant. So why don't we break that down further? We have E equal to the integral of k lambda dy over, and we can say this is going to be, now we don't really have to put xi or yi, let's just do x and y to keep things simple. So get rid of this y. So now we have r squared, which is just going to be x squared plus y squared. And then it's going to be times that unit vector, which is x negative y, and then the square root of x squared plus y squared. Okay, but K and lambda are constants. So we can factor that out, and we have E equals to K lambda times the integral from negative a to a of just dy over, now x squared plus y squared to the power of 1/2 times half is just 1, and then now you have another 1/2. So 1 plus a half is going to be equal to x squared plus y squared to the power of 3 over 2 x negative y. So that is what you would have for now. And because you have an x component and a negative y component, you have to separate these two and calculate them differently. So I want to write down, we need to solve for ex and ey separately. Now, one thing you can do is first take a look at what happens with each of these. Do we want to do the work and solve for ex and ey, or maybe we can see if we can just ignore one of them? So what I would do in this case is take a look at one component here, which is my dy. I take a look at the exact same component down here. So this would be, let's say, dl. Now with this, or not dl, but dy prime. So if I have this, that means that from this point in the bottom part of the rod, I'm going to have a differential electric field element going up this way. So this is dE prime. Now taking a look at this, I have components that I can compare between the two, and it looks like the vertical components are going to cancel out. So what this tells me is that by symmetry, the y components cancel. So we know only, dex counts towards dE. So in this way, we can just get rid of ex completely, or ey completely. So this one is just 0 by symmetry. So this is the type of analysis that you can do to try and reduce the amount of work and the amount of math required. So let's try to solve for ex. I know ex means that I just have to care about the x component. So that means I have k lambda, and I have the integral from negative a to a of x over x squared plus y squared to the power of 3 over 2 dy. And this is all in the x hat direction. Now, in terms of this, you may have to use trig substitution in order to move forward through this. This is not a math course. I don't mind if you use additional tools to help you get there. But essentially, what you can do is use trig substitution and have tangent of theta is equal to y over x. And then you have y is equal to x tan theta. And then you have dy, which you differentiate, and it becomes x secant squared theta d theta. in this case, what I can do is then have EX be rewritten as K lambda. Solve this based on theta 1 to theta 2, because I've done a change of variables. I know dy is x times secant squared theta d theta, so let's do that, x squared secant squared theta d theta. I now have to figure out what this denominator is going to turn into, and so I actually can say secant of theta is equal to hypotenuse over adjacent, which is equal to the square root of x squared plus y squared over x. If I do this, I can, for x, I can say the square root of x. Let's say square root of x plus y squared is equal to x secant theta. And of course, x squared plus y squared to the power of 3 over 2 is simply just 1/2 of this cubed. And I now have a new relationship that I can use to replace this. So this is x cubed secant cubed theta. And all, of course, in the x hat direction. Now, how do I simplify this? I now have EX being equal to K times lambda integral of theta 1 to theta 2. And we actually have, we can cancel out a lot of things. We have x squared canceling out the cubed over here, and we have secant squared theta canceling out the cubed here as well. And we end up with a simple 1 over secant theta d theta x hat. But secant of theta is actually hypotenuse over adjacent. So if we do 1 over secant, it's just adjacent over hypotenuse, which is cosine. So that's the next step. Make this simpler. We now have EX is equal to K lambda integral of theta 1 to theta 2 cosine theta d theta x hat. Now the problem is actually solving for this. What is theta 1, theta 2? As an aside, we can say at the very bottom, negative a is going to be considered theta 1 to positive a, which is theta 2. So that means sine of theta 1 of theta 1, and if I don't want to scroll up again, but it's going to be a over the square root of x squared plus a squared, and then negative a over square root of x squared plus a squared, because it's going down. And then you have sine of theta 2 being equal to a over the square root of a squared plus x squared. Okay, so what do we do next? We just keep solving. K times lambda. I know that the integral of cosine is sine, and so I have sine of theta 2 minus sine of theta 1 x hat EX is equal to K times lambda. Sine of theta 2 and theta 1 are the ones that we just solved for, and we know that it's going to be a minus a over the square root of x squared plus a squared. And that's going to be in the x hat direction. So the final answer, we then have 2a k times lambda divided by the square root of x squared plus a squared in the x hat direction. And I think I made a mistake somewhere because it seems like I'm missing something. And I forgot to take out the x up here. So over here, there was supposed to be an x that was taken out, not in this step, just in here because of this. So let's just make sure we've added that x over. Now let's just make some room for this because we want this to be our final answer. Okay, so that is our final answer, and we are done. Now that we've covered a uniformly charged rod, we want to cover something that's outside of the Cartesian coordinate system. Maybe we want to look at the polar coordinate system. So let's take a look at a charged ring. Keep in mind, a charged ring still has a linear charge density, but it's just in a circle. So the question says, a uniformly charged circular ring with a linear charge density of lambda and a radius a is in the YZ plane centered at the origin. Find the electric field at any point P on its x-axis. So first step is drawing a diagram, and it's very important to understand that we have to break up this ring into many small components. So over here, we've broken it up into a small component as an example. So this tiny piece here, that is going to hold a charge dq. So it's important that we find dq and then we find dE. So first step, let's just say this holds a charge of dq, and it's going to be equal to some rho L dL. Now this time it uses dL, but rho L is still lambda for the charge density. So we have lambda dL, but dL is an arc length. So we have to make sure it's the radius times the change in angle. So this means this is lambda, and then a d phi, like that. Okay, so now we can move forward and keep working on this problem. It says determine values and the bound for integration. Well, to make things easier on us, why don't we take a look at whether we can cancel out anything first. If I have a component from here going down, and then I have a component from here going up, then it seems like no matter what, I'm going to have a circular contribution of dE's. And so on the xy plane, or not the xy plane, the yz plane, everything should cancel out. So that means any point on here will cancel out a point over here, so on and so forth. So from symmetry, only dEx remains, since all dEy's and dEz's cancel each other out. So that makes life a lot easier for us. It means that we just have to solve for dEx. So now let's try and figure out dEx. it's going to be K dq, just like before, over some sort of Ri squared in the Ri hat direction. And specifically, it's dEx, so it's in the Rix hat direction. So we can use what we've learned before. We know that Rix is equal to x over the square root of x squared plus y squared in the x hat direction. We also know from before that dq is equal to lambda a d phi. We also know that Ri over here is simply, the square root of x squared plus y squared, if we just consider it to be r. So dEx is just simply going to be k, and dq is going to be lambda a d phi divided by x squared plus y squared times x over the square root of x squared plus y squared x hat. So let's try to simplify this even further. We have dEx being equal to k lambda a d phi. Let's put an x in front here. And then we have x squared plus y squared to the power of 3 over 2 in the x hat direction. Now the next step really is to just integrate. But first, we need our boundaries, and we know that we're going to have to integrate with respect to phi. And for d phi, we know that it starts at an angle of 0, so 0 degrees, and then moves all the way around back to 2 pi in radians. So it goes from 0 to 2 pi because it goes in a full circle. So now we can go ahead and try to solve. Okay. We can have Ex is equal to, let's factor out all of the, actually wait, let's just do this first. 0 to 2 pi of Ka lambda x divided by x squared plus y squared to the power of 3 over 2. Then you have d phi x hat. We then can factor out all of the constants. I usually like to highlight them. These are all constants. So we have, and in fact, all of these are constants because x and y are not dependent upon phi. So you end up with a lambda kx over x squared plus y squared to the power of 3 over 2, integral of 0 to 2 pi of d phi in the x hat direction. That's just simply going to be a lambda kx over this. And the integral of 1, because we can assume there's a 1 in here, is just going to be theta. So we now have theta from 0 to 2 pi in the x hat direction. We have x squared plus y squared to the power of 3 over 2, and this is then 2 pi minus 0. And so our answer would be 2 pi a lambda kx divided by x squared plus y squared to the power of 3 over 2. So this is all in the x hat direction, and that is our final answer. So we've gone through two problems with linear charge density. We had a rod and we had a circle or a ring. now we want to take a look at the next level up, and that's going to be a solid surface, or basically any type of area surface. So we're going to take a look at a uniformly charged disk. So in this problem, we have a uniformly charged circular disk that has a radius of r and a surface charge density of sigma. Now, find the electric field along the axis of the disk. Along the axis of the disk just means that if your disk is laying in the xy plane, then the axis is actually where it's spinning around, and that would be the z-axis. So step 1, draw a diagram. Diagram's already provided to us, and we have the following. And let's just see. We do have to label DE somehow. And right now we can see that if we take a look at the orange charged disk, we've highlighted a blue ring around here that signifies a portion of that disk. So there are two options when going about an area. First, you can do something like this, where you have some sort of dr, and then you have rd phi, for example. Or you can take advantage of dr and actually get the entire circumference of the ring. So you have almost like a little, so we have dr over here. Oops, that would be dr, the thickness of the ring, and then the circumference of the ring. So if you break open the ring from here, you end up with a long rectangular strip. That is dr. And then you end up with this being 2 pi r. And that gives you some sort of area. So there are multiple ways of solving this, but the easiest way is to make things simpler for us. And that means getting the easiest area to solve for. So taking a look, we do want to determine the values and bounds for integration. So by symmetry, the electric field due to the ring, does it cancel anything? So if I have a piece of the ring over here, and I know that DE from this left side, let's do DE from the left, and then we have another piece on the right side. Oops, we have DE from the right side. This tells me that DEX and DEY are going to cancel each other out. So anything on the XY plane will cancel each other out because there is an opposing DE component from the other side. The only thing that can't cancel out is the Z component. So that means that DEZ is the component that we're going to be looking for to solve. So by symmetry, let's just write this somewhere else. Only DEZ remains. Now, when we're dealing with integration, we want to find the easiest way to get to the answer. So each mini ring has a radius of r and has a charge of dq. So we can consider one entire blue ring to have a charge of dq, and it's going to be sigma, the surface charge density, multiplied by the area. So remember dq, and the question already gives you the answer, but I'll show you how to derive it. dq, because this is an area question, is equal to rho s for the surface charge density times some sort of ds. Now, rho s is given to us as sigma, like this. And ds, well, ds is just some sort of area. And in our case, ds is this entire ring. So one entire ring is going to be equal to 2 pi r multiplied by dr. So we have 2 pi r dr as our dq. So then what do? We have dez is equal to k dq divided by the square root of, and now let's take a look at what we should actually use for this. R is this distance, and it's going to be, let's go back a bit. We're looking for this distance because that's technically our R, the distance from the ring to point P, and so this is going to be the square root of R squared plus Z squared. And that's what this is. So it's R squared plus Z squared squared. Now we want the Z component. And the Z component is going to be, we have to think about it a little bit. We have X, Y, Z. And in terms of the Z component, it'll simply be Z over the square root of R squared plus Z squared in the Z hat direction. So overall, we end up with dez is equal to k dq. And in this case, we have 2 pi, or k, 2 pi r sigma dr, z divided by r squared plus z squared to the power of 3 over 2 z hat. Now, where do we integrate? We are going to integrate with respect to dr. So dr, this is going to be the bounce. We're going to integrate from 0 all the way to, it says, a radius of little r. So we'll just do 0 to r. And that should give us the answer. So let's go on to the next page and continue from there. So we have E being equal to the integral from 0 to r of 2 pi kr sigma z divided by r squared plus z squared to the power of 3 over 2 dr and z hat direction. Now let's first factor out everything that's a constant. So that's 2 pi k sigma z. And we do have the r in the denominator, so we can't factor that out. So we end up with E is equal to 2 pi k sigma z integral from 0 to r of r over r squared plus z squared to the power of 3 over 2 dr in the z hat direction. And we can use the exact same thing as before with trig substitution. I won't really go through the entire steps here, but you end up with 2 pi k sigma z. We have to change the bounds from theta 1 to theta 2, and we end up with, just like your x tan, we have a z tan theta, z secant squared theta d theta divided by z cubed secant cubed theta z hat. So just keep in mind, to go from here to here, we made an assumption that tan theta is equal to r over z, just from here. And then we have, oh, theta's here, so you know. So the tan theta would be opposite over adjacent. And then you would have R is equal to Z tan theta. And then you go from there. Now you have E being equal to 2 pi sigma ZK divided by, let's see what we can factor out. I know that we have a Z and a Z, and we have a Z left at the bottom. We also have secant squared, so the cubed disappears at the bottom, so we end up with a Z that we can factor out, and then integral from theta 1 to theta 2 of tan theta over secant theta d theta Z hat. But we know tan theta is equal to opposite over adjacent, and secant is equal to 1 over cosine. So this is actually equal to, so this part, sine theta. So we can go from there as the next step. Oops. So E is equal to 2 pi let's see. Sigma k, and then we have, the integral from theta 1 to theta 2 of sine theta d theta. I'm just taking a look over here to see what else we have. Right, so just, I wanted to just share one more step here. After we took out the Z, we can also cancel out these two Z's, so they're no longer important. So moving on, we have E equals to 2 pi sigma k. You have negative cos theta as the integral of sine theta, and they're going from theta 1 to theta 2. This is all in the Z hat direction. And just keep in mind, as an aside, we do have to define theta 1 and theta 2. So 0 was theta 1, and then R became theta 2. So cosine of 0 is equal to 1, and cosine of R is equal to Z over Z over the square root of R squared plus Z squared. Oh, not cosine of theta 2. Okay, so now we have E being equal to 2 pi sigma k. This is going to be minus cosine of theta 2, which ends up being you can actually factor a negative out here. You'd end up with minus cosine of theta 2 plus cosine of theta 1. Let's see. Whoops. Z hat. This is equal to 2 pi sigma k. And then you end up with 1 minus Z over the square root of R squared plus Z squared in the Z hat direction. So that's your final answer for the electric field a certain distance away from the disk itself. So we've done a few calculations and problems with being able to calculate the electric field a certain distance away from different types of shapes and symmetries. So in problem 4, we found out that for a disk of radius r, the electric field a point P away from the center of the disk was given as follows. So if we want to take a look at the electric field of an infinite plane, why don't we just make that disk extremely large? So that's what happens when r approaches infinity. So we're trying to make a disk of a certain radius and make it extremely large to make it an infinite plane. So if we take a look at that, we then have this term going towards a very large number, which means this is just going to go to 0. So in that case, we have 1 minus 0, or essentially 2 pi sigma k, and this whole thing is just 1. So we end up with 2 pi sigma k, and just remember k is also 1 over 4 pi epsilon naught, so we can replace that and end up with sigma divided by 2 epsilon naught. And what's great about this is that for an infinite plane, note that the answer is not even dependent upon the radius or the distance away from the plane. So this tells us that for an infinite plane, the electric field is constant and uniform any distance away from that plane. So next, let's take a look at electric dipoles. The electric dipole will consist of two charges of equal magnitude but opposite signs. So a good example is water. You have a positive area where the hydrogens are and a negatively charged area where the oxygen is. So we can represent that using a little bar over here with a negative and positive end. So many molecules can be modeled as dipoles, and it can actually be used to explain molecular behavior. So you'll see as you study and move on through either biophysics, life physics, or medical physics, that a lot of examples within the human body or in chemistry will result from electrostatic interactions between different molecules in our bodily systems. So now that we have a representation of a water molecule or some type of molecule as a dipole, we can calculate the electric field a certain distance away from that dipole. So next we're going to go through an example where we do try and calculate the electric field a certain distance away, kind of like here, from this dipole. After discussing what an electric dipole is, we do want to be able to calculate something with an electric dipole. So a molecule may be modeled approximately as plus q at x equals a, and then minus q at x equals negative a. So at these 2 points. We want to find the electric field on the y-axis and an expression for when y is much greater than a. So we have a diagram that's already drawn for us, which is great. And the one thing that's different here is the difference in charge. So it's important to know that if you have a minus q charge over here and you have a point over here, there's going to be an attractive force. So therefore, this electric field coming from the negative charge is going to point towards it. For the positive q, you now have an electric field that's pointing away from it. So keep in mind when you're drawing these diagrams, make sure you have the DEs pointing in the correct direction. So we know that there's only one component involved after we draw the diagram, because we know that the y component cancels out because we have essentially this going up and this going down. So the only thing left is in the negative x direction. So we can pretty much say that by symmetry, oops, if I can spell symmetry, by symmetry, only the x component remains, so only the negative x direction remains, and we can say DE y cancels out. So next, we want to take a look at the electric field itself. So E is equal to KQ over R squared. And we have to take a look at the X component. So we take a look there. We know that for R, which is going to be here, and here we have R plus, and we have R minus. We know that R plus or minus is essentially equal to, you have plus or minus A, and then 0 as the Y component, because the that component just cancels out. So therefore we only have to worry ourselves with this, just the X component matters. Save us some work. So in this case we have times negative A over R plus K negative Q over R squared times plus A over R in the X hat direction. Oops. Okay. Now just remember, for an electric dipole, it's really not a charge distribution. Rather, we're considering it as 2-point charges. So we have to use the principle of superposition. So that's fairly important here. So I'm just going to write down must use. Because it's 2-point charges. Charges, not a continuous charge distribution. Okay, so continuing on, we have E being equal to, we can add the two of them up and we end up with minus 2 KQA divided by A squared plus Y squared, Y squared to the power of 3 over 2. Why? Because, and let's put this in the X direction, since R is equal to the square root of A squared plus Y squared, since this is A and that's Y. Okay, so that is actually the answer. We don't even have to do a lot more here, but there is a follow-up. What happens when Y is much greater than A? Well, when Y is much greater than A, then you end up with, E being approximately equal to minus 2 KQA divided by, and if we have Y being a lot greater than A, the A term essentially may go to 0 within the denominator, and you end up with Y cubed in the X hat direction. So that it would be the answer, just in case Y is much greater than A. So what does this mean? It means that the dipole really has no net charge. So at large distances, its field cannot have the inverse square drop-off of a regular point charge field. So let's just say a dipole field falls faster than a point charge. Since E is proportional to 1 over y cubed, whereas usually you would have 1 over r squared as the drop-off. So with electric dipoles, there also comes electric dipole moments. We represent that using P. So that's the product of charge Q and the separation D between the two charges of the dipole. So in problem 5, we found out that when y is much greater than a, that the electric field is equal to 2kqa over y to the power of 3. So this charge separation was 2a, so we can actually say that P is equal to 2a times q, so the d actually becomes 2a. And now we can actually have a condensed equation where we have E is equal to kp divided by y to the power of 3. So that's just a shortened equation that you can use moving forward. In terms of electric dipole moment, it is important to understand that it is a vector quantity. So dipoles depend on both distance and orientation. The dipole moment has to be considered a vector with a magnitude of qd in the direction from the negative to positive charge within the dipole itself. So this is just a diagram to represent that if you have a dipole where it's still one molecule or one object, just with a negative or positively charged area, you now have a dipole moment pointing from the negative to the positive direction, and you have a dipole moment associated with that. So now we'll take a quick look at what happens to matter in electric fields. So the behavior of matter, especially charged matter, is fundamentally determined by the electric field that it exists in. So one example is electron movement through parallel charged plates. So this is one example here where there's a positively charged plate at the top and a negatively charged plate at the bottom. Now you have an electron in the middle and you're forcing it to go through these two plates. Now, between these two plates, there has to be an electric field. And that electric field is going to cause the electron to move, to stray from its path. So as it enters here, the electron, which is negatively charged, is going to be more attracted to the positively charged plates. So it's going to go across and then move upwards more and more until it exits the parallel charged plates on an angle. Where can this be applied? It can be applied in electrostatic analyzers, and also the behavior of matter, specifically dipoles, will also experience a torque or some sort of spin if it's in an electric field. So just some things to keep in mind as to how electric fields can affect the behavior and motion of matter. So point charges in electric fields, when we combine a single charge motion, which is just simply force is equal to mass times acceleration, with an electric field where force is equal to q times e, we can now determine the acceleration of a particle with a specific charge q and a mass m by equating the two of these together. So you're going to end up with ma equals to qe, and you end up with the acceleration being equal to qe over m. So if we take a look at this, it tells us what a charge to mass ratio will do. The smaller the mass, the larger or the faster the acceleration. So a lot of X-rays and cathode ray TV tubes make use of these electrons that are accelerated in electric fields so that we can take advantage of this phenomenon. So I want to wrap up with what happens to dipoles in electric fields, because it is something that is very common to come across in life and medical physics. You have molecules within your body, and most of them are pretty much going to be modeled as dipoles. So if you're looking at an MRI, or if you're looking at other sorts of electromagnetic phenomena within the human body, or if your human body goes through an electric field, then your dipole will react, or your molecules will react. So a dipole in a uniform electric field, so just remember, this is your dipole with a dipole moment, it's going to experience a torque. And so a torque is defined as R, the moment arm, cross multiplied, by the force applied. So this is the force that's being applied in a certain angle. Now, we won't be testing you on this, but the torque that comes from a dipole is simply going to be from the moment arm, which is the dipole moment, multiplied by the electric field. And the electric field is a certain, has a certain direction. The dipole moment has a certain direction, and therefore these two will give you the dipole moment torque. There's also work and energy involved, and so if you are interested in doing any calculations with dipoles and electric fields, these would be the three equations to use.